This is the presentation recording of our paper titled Intelligent Camera Selection Decisions for Target Tracking in a Camera Network. Target tracking in a camera network is an important application in computer vision. So for example, consider that this is a trajectory of a target in camera CI, and at time 4, this target leaves the camera field of view of CI. And then to keep track of the target, we first need to identify when the target will reappear in the camera network. Let's say after time tau, it reappears. Then in which camera it is most likely to reappear, let's say in camera CJ, and then where in this CJ so that we can track the target in this single camera. So camera selections are shown to be crucial for efficiently tracking targets in a camera network because these make only one decision at a time, and these reduce reliance on re-identification. They also don't require any information from the camera network like its camera network topology. So these methods maintain a state vector, so which contains observation or last seen location of the target in terms of C camera, B bounding box, del B, the difference between two bounding box locations, and the time information, time since the target is last spotted in the camera network. The camera history, the history of cameras queried. So at time t, the state vector maintained by these methods is this. So we first make an observation that action history is an important state variable for camera selections because it influences the decision of which camera to select next. But retaining longer history in these methods is computationally expensive. So in this regard, we make the following contributions. We first use state representation learning to represent action history in a small latent representation, and we'll also show that it provides performance benefits. We make semi-supervised training of the camera selection policy, and which makes our method to not rely on the large annotated data. We demonstrate the performance on 4 real data sets. So this is our system architecture. Let's just first see this encoder-decoder architecture, where the encoder encodes the camera history in a small latent representation using 2-stage LSTM, and the decoder decodes it. So during inference, this decoder is dropped and only the encoder is used to encode the action history. So this is our architecture in which from the multi-camera stream, we create this state vector as shown in one of the previous slide. And then using the 3-layer neural network, we learn a Q-learning policy to predict the Q values corresponding to each camera index. And we select a camera which has the maximum Q value so that we can make a re-identification query to identify the spatial location of the target. This process is repeated again and again so that we can identify the trajectory of the target in the camera network. This table shows the performance when we use the autoencoder. When we don't use the autoencoder or AE, then in around 25,000 episodes, we achieve the PCH of 53.6, where PCH is percentage camera handovers. When we use an AE, which is trained on the same dataset, then in 21,700 episodes, we achieve a PCH of 65. Seeing this performance benefits, we train the AE once with a larger camera network of 40 cameras, and then we use the same trained encoder for all the smaller datasets. These last 3 rows shows when we train on a network of 5 cameras, then in around 25,000 episodes, we achieve a comparable PCH on different sequence lengths. So that means AE provides performance benefits and also saves the training time of the policy because we are not retraining the AE for every dataset. So this is the semi-supervised training procedure. In this figure, the first row shows the time information. The second row shows the camera selection policy. And the third row shows the reward given during the training in an episode with frame skip value of 5. It means that every 5th frame receives a reward and all other frames are skipped. So during backpropagation, to compute the target vector, we use discounted reward, which is computed by multiplying by gamma. That means gamma R, gamma square R. And where the camera selection is not equal to the camera where the reward is provided, then it is used as a 0. So this way, we train our policy in a semi-supervised way with only 1/5 of the annotations. And hence, we don't, our method don't rely on the large annotated data. So this is the performance using precision and F1 score on 2 data sets. And neighbor is a method which uses the camera network topology, and steps is another related method. And our method achieves state of the art on both of these data sets. So the last row shows the semi-supervised trained approach of our method, which is better than the 2 related methods and is also comparable with our supervised training policy. The results on all other data sets is shown in our paper. Please refer to that. If you have any queries, please contact us on this email ID. Thank you.